Welcome to Organic and Biochem. We're going to start this with an introduction to organic chem, and then we'll move later in the semester, about halfway through, to talk about biochem. And it's going to be tons of fun, so I hope you're ready. Oh, I might have a different idea of fun than most of you. So way back when, let's talk about some history. No, I'm just kidding. I won't talk, I'll try not to talk monotone, but yeah, right in the early 1800s, maybe around 1830 or so, Frederick Fuller obtained urea artificially. Well, prior to this time, people thought you could not obtain organic compounds without starting with some type of organic living organism, some type of thing with this, what they called this spark, that it needed a living spark in order for you to have organic compounds. However, um, Frederick Fuller was trying to create ammonium cyanate by starting with silver cyanate and treating it with ammonium chloride. And he did do that, but it only stayed around for a little while and then it moved on to urea, which, lo and behold, is our now ability to make organic compounds without organic starting products. So this was the first time that we were able to make an organic compound starting without living organisms. Since then, we've changed the definition of what organic chemistry is, so now it's the study of carbon-containing compounds. Organic compounds are made up of more than carbon, though. They have carbon and hydrogen and oxygen and nitrogen, but we also have sulfur, phosphorus, and sometimes some halogens. There are some other compounds, or excuse me, elements that we'll talk about, but there are some compounds that are made up of these elements that don't count. So if you remember from from inorganic chem or gen chem, you remember CO3 2- is a carbonate, and we have carbon dioxide. Those are not considered to be organic. They are considered to be inorganic compounds, so we do have some exceptions. Now, biochemistry, what we're going to study later on, we're going to learn all about these organic compounds, and then we're going to learn how they work within living systems. So that's our biochemistry part. So chemists have actually discovered over 10 million organic compounds. Now, if you remember those elements we just talked about, carbon, hydrogen, oxygen, and nitrogen, then we said phosphorus, sulfur, and maybe some halogens. So maybe 8 to 10 elements in total make up over 10 million compounds. Now, what are there? 118 elements? So we have the other 100 or so elements that really only make up 1.7 million compounds. So why the vast difference? Well, carbon can bond in so many different ways to itself, to other compounds. It can form single, double, and triple bonds, which allows us to make all these different compounds, synthesizing over 10,000 new compounds every year. They're in everything that you do during the day, whether you eat your food, the clothes you wear, the medicines you take, the soap you use in the shower, or the dishes, or something like that, the pesticides we spray, the gas you put in your car to get anywhere. And what do we do to purify our water? Most of these involve some type of organic compound. So looking where these are on the periodic table, the purplish area are metals. I apologize if you're colorblind. Hydrogen, carbon, nitrogen, and oxygen, phosphorus, sulfur, and these are the halogens, if you remember that. Now, does that mean we don't use any of the other ones? No, they're just not as common. But if you look at your vitamin bottle, I'm sure that there's some chromium and some copper and some zinc and some iron. If we don't have iron, right, our hemoglobin wouldn't be able to form. So we do have these other trace elements that we use, but for the most part, and this is an old periodic table because there are, all the way over to 118 now, but we use only, 8 to 10 compounds regularly. I said compounds, excuse me, I meant elements. So we use about 8 to 10 of these elements regularly. Back from Gen Chem, so this is your little Gen Chem review. We need to know the difference between intramolecular forces and intermolecular forces. So intramolecular forces, intra means within, and those are our bonding forces. So you would have learned about those as we have two major types of bonds. We have ionic bonds, covalent bonds. Maybe you talked about metallic bonds. We're not really going to talk about metallic bonds a lot because we're not talking about very many metals here. And most Gen Chems just really brush on metallic bonds. You don't really get into that till later in inorganic chemistry classes. But intramolecular forces are the ones that happen within the molecule itself. What holds that molecule together? So these are going to be important. Remembering main difference between these is that ionic bonds transfer electrons, and this is my shorthand for the electron, and we form a cation, which is electron deficient, and we have an anion, which is electron rich. So we have these two cations and anions, which are attracted through electrostatic interactions, or what are opposite charges, right? Now, covalent bonds share electrons. So these are going to be sharing electrons. Sometimes they share them equally, sometimes they don't, but this is what gives rise to the polar and nonpolar that we're going to have to talk about soon in a minute. So intra means within. So if you have an intranet, you can only get on it from work or at school. You have to have a special card or a special login. You used to have to be at the facility, but we've come a long way. So you need to have some type of special network access in order to get into that internal network. Now the interwebs, we'll call it, because that's the new word on the street, right? Although, who knows? So the interwebs or the internet, if you will, we can get to the whole world. We can get anywhere we want. The world is at our fingertips. But this is just going to be how molecules interact with each other. So one molecule interacting with another molecule, what holds them together is going to be our intermolecular forces. Now, I'm hoping that you talked about that in Gen Chem, but if you didn't, you should go back and review that. I'm going to review it very quickly. So intermolecular forces are our non-bonding forces. These are going to be responsible for our physical properties. To go back a slide for a second, these are responsible for chemical properties. So our physical properties like melting point and boiling point and density. Okay. Also, how are they going to, let's see, what else do we talk about? I don't know, it's all that's coming to me right now. I'm sure there's more, but when you're recording yourself, you can never remember what you really want to talk about. So in our intermolecular forces, our non-bonding forces, we are going to see that we have nonpolar or polar that come to light. So this is with our covalent bonds. We need to ask ourselves first, what is our molecule? Is it polar or not? Is it polar or nonpolar? And I just noticed a typo down here. This is not electronegativity. It should say electronegativity, so this should be a V. All right. So what we need to look at is that electronegativity difference. So En, I'll show you an electronegativity chart on the next slide. You may remember doing this back in Gen Chem where you take, okay, well, if chlorine is 3.5 and 3.5, so you subtract them, their difference is 0. This is going to be a nonpolar bond. Anything bonded to itself is nonpolar. Now, carbon is going to be what, if I remember correctly, 2.5, and hydrogen is 2.1, so the difference is 0.4. Oh, I have it written right here. 0.4. It's considered nonpolar. I mean, some books might say that, oh, anything over 0 is polar, which is true. I mean, it's not that it's not true, that it does have a slight unequal sharing of these electrons, but for multiple reasons in organic chemistry, we don't consider that to be polar. Most of our compounds are going to be made up of carbon and hydrogen bonds, so even if they were polar, they would cancel each other out. So any slight polarity is probably going to cancel themselves out throughout the molecule, but there really isn't enough polarity to change the shape of the molecule. All right, so polar bonds, however, we need to kind of look at that. So this is going to be kind of a basic inorganic chem. So we can look at, okay, is carbon bonded to oxygen? Is it bonded to nitrogen? Is it bonded to, and we use an X for halogens, just in case you don't know that. So X would be maybe a halogen, maybe a chlorine, or, a fluorine. We don't get a lot of, it depends on what we're talking about. So we look at the electronegativity difference. This is our electronegativity chart. I'm not going to spend a lot of time on this. Hopefully it looks familiar. But this would be something that you would be given if you needed it. Usually in Gen Chem we need it. Again, here we're going to be looking at more of just overall, is it bonded to oxygen? Is it bonded to nitrogen? Is it bonded to fluorine, chlorine, something like that? It's going to be pretty obvious what we're talking about, but we'll learn about it for each individual functional group, so you'll be able to take a look at it that way. So again, depending on where you took Gen Chem and what you were looking at, everybody kind of has a little different values. I mean, the ones that I usually work off of are 0 to 0.4 are nonpolar covalent, 0.5, and I say to 1.9 or 2. It depends where we're teaching at is polar covalent, and anything greater than 2.1 is ionic. So this is just a general guideline. So it's not cut and dry. Remembering, again, back from Gen Chem, the different types of structures. So you probably learned about Lewis dot structures. If you didn't, then I worry about your Gen Chem experience, and maybe we should talk about doing some review. But a Lewis dot structure should have dots. Okay, those are there to show the lone pairs of electrons, and they are important. Structural formulas, these are all structural formulas for the most part. I mean, this one is written a little bit differently. When I talk to my students about ethanol, I just talked to them about it the other day in Gen Chem, and they're like, why did they put this hydrogen over there? Is it just to, screw me up? And I said, well, no, because if it was written like this, CH3, CH3O, you could have multiple different structures with that particular, you could have CH3 like this. They're called isomers, where we have CH2, and then we have the OH, or we could have the CH3. I guess I could have just pointed to it. I didn't remember it was up there. And we could have the oxygen in the middle and have a completely different functional group. That's supposed to be an H. So this is an ether and this is an alcohol. And they act, I shouldn't try to talk and write at the same time, they act differently. So even, in Gen Chem, it was just maybe we were calculating molar mass or something like that. It didn't really matter on that structure as much until you got to this point where we're starting to talk about intermolecular forces. This is going to have a hydrogen bond, and it's going to have a much higher melting point or boiling point than the ether, which does not have a hydrogen bond. So while this is polar, it's got it's got dispersion forces, and it has dipole-dipole, but it doesn't have hydrogen bonding, where this one will have hydrogen bonding. So it is going to be important to be able to draw structural formulas. We're going to be drawing a lot of structural formulas. So I'm kind of hoping we can all get to the point where we can draw the line structures. The most difficult thing, and we'll go through how to draw them, but the most difficult thing with this is making sure that you have enough carbons when you mean to, and not too many. So you can be easily to make a mistake. So you always want to double check. So this is considered a condensed structure. You can condense things even more. You could say you have CH3 and I have CH2 5 times, and then I have CH3. So you can put parentheses around it like that if it's a longer molecule. So more on intermolecular forces. I just mentioned dipole-dipole, hydrogen bonding, and London dispersion. These are the three what we call van der Waals forces that we talk about. In inorganic or Gen Chem, we do generally talk about them, at least when I teach it we do, so hopefully you have some experience, but these are definitely weaker than our bond, I mean to cross that out. They're weaker than our bonding forces, but they still do play a large role in what's happening. We do have another one that's called ion dipole. So if you are, dissolving, this would be like water, if water is polar, right? So it has dipoles. So if you're going to dissolve like sodium chloride in water, you're going to get ions, the sodium ions and the chloride ions that are going to be attracted to, the hydrogen, the partial positive, and the hydrogen. The partial negative will be attracted to the sodium ion, and so on. So we're going to get stronger intermolecular forces from something that is containing both ions and dipoles. This isn't something that happens a lot. Well, I guess it could. It depends what we're using. But know that this one exists, but it doesn't come up as much. We don't talk about it as often. And again, these are all the results of unequal sharing of electrons. Even our London dispersion forces, or sometimes people don't include London, they just say dispersion forces. That's fine. I'm okay with you saying LDF, H bond, dipole, if whatever. Just as long as I can understand it, but I need to understand it. And since we haven't met in person, I'm just going to try to give you some of the shorthand I use. These increase with increasing size. These increase with increasing electronegativity difference. I'm sorry, I meant to say dipole, but hydrogen bond, remember, is only between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. It's not just hydrogen bonded to anything. And it's these three elements because they have a greater electronegativity difference than anything else, plus with their size. So it does make a bigger difference. So what are the physical properties that we're going to talk about that are different from these? Well, melting point and boiling point. So if we're talking about what happens to the melting point and boiling point, the heat, actually adding heat, causes the bonds to vibrate. Well, bonds are always vibrating. So when we measure bond length, we measure a median difference between the shortest and the longest. So this would be the shortest, this would be the longest. We measure the somewhere in the middle of those two, and since we can't actually see the bond, we measure the difference. So we take and we measure from the center of each atom, and then the center of each electron cloud the best we can, and then we take and divide that by 2. But when they start vibrating faster and faster and faster, they can break the spring, which is the bond, and that's when we get to go to a higher that's when they go to a higher temperature and they become, a phase change. So maybe if we're going from a liquid to a gas, they start to go in as like a vapor up in the air. So there's a stronger attraction to each other. It's going to be a higher temperature that's going to be required to break those bonds. So it's going to be a higher melting point or a higher boiling point. So polar molecules having both dipole, and London dispersion forces are going to have higher boiling points. And if they have, hydrogen bonds on top of it, they're going to have even higher boiling points. So what we want to look at first to answer these questions, which of these compounds has the higher melting point or boiling point, you want to first ask, is it polar or is it nonpolar? Well, I guess the very first question should be, is it ionic or covalent? We don't have a lot of ionic compounds in organic chem. Most of them are going to be covalent. But then you want to ask after that, if it's ionic, it's always going to win. So ionic will always have the higher melting point, boiling point. But after that, you ask polar or nonpolar, polar is always going to win. But you have to ask, what intermolecular forces are present. And if it's just LDF, everybody has dispersion forces. Every single molecule has dispersion forces. If that's all they have, the larger they are, the more they'll have. Because we're talking about, if you remember talking about that, hopefully, how easy is it to disturb the electron cloud? That's called polarization. So how easy is it to distort the electron cloud? Well, the larger it is, the more easy it's going to be to distort that electron cloud. Then we have the dipole, and those are going to be based on, again, electronegativity difference. But if we have both of those, we're going to definitely have a higher melting point. And then if we have hydrogen bonding on top of it, we're going to have an even greater melting point and boiling point. So one more thing here about this, solubility. Like dissolves like. When we talk about that, we're talking about polarity. So again, we have to be able to tell if a molecule is polar or nonpolar. Polar molecules dissolve polar molecules, nonpolar molecules dissolve nonpolar molecules. I'm sure you've, heard of oil-based paint that we have to, clean with mineral spirits. But, in a pinch, you can clean your hands with gasoline, but I don't recommend it because those are nonpolar molecules. But polar molecules, we need to use polar compounds. Now, water works well because that's why it's considered the universal solvent. It is polar and can, for its size, carry off a lot of different, it can actually dissolve many different types of compounds. Let's see. So nonpolar molecules, again, only have the dispersion forces. Polar molecules can have dipole-dipole and hydrogen bonding. And they also have the dispersion forces as well. They can form weak bonds to polar molecules. This is important because oxygen dissolves in places it shouldn't, like water and blood, which is important, but it doesn't dissolve enough, which is why we need our hemoglobin. But why is carbon monoxide so bad? Well, carbon monoxide is more attracted to our hemoglobin than oxygen due to the bonding site. And so it would preferentially bond to carbon monoxide rather than oxygen, and you slowly drift off to death. So that's why we don't want that to happen. Okay, so make sure you check your batteries and your smoke detectors and your carbon monoxide detectors. Public service announcement. All right, so organic molecules often have both polar and nonpolar regions. So rule of thumb, one polar functional group can carry about 5 to 6 nonpolar carbons into a water solution. So what that means is, so if we have, let's just say, what do I want to say? Let's go with pentanol. If I go with pentanol, that's a 5-carbon alcohol. You're not necessarily going to be able to discern that with your eyes. So in lab, about 4 carbons, we start to think that maybe it's actually not dissolving, but it will dissolve about 5 to 6, but you might not be able to really see that with your eyes. So about 4 carbons, your eyes are going to be like, no, it's kind of iffy. But ionized groups actually can carry about 18 carbons or more into solution. So these are going to be our acids, the acids that we talk about. So we have carboxylic acids, things like that, that can form ions, which I said, we don't have a lot of ionic type compounds, but we do have functional groups that can form ions. And those can carry about 18 or more carbons. So again, rule of thumb, this is not tried and true. I'm not, that shouldn't be what I said. It's not true every time. It's not going to be, oh, it's got 5 to 6 carbons, it's always going to carry it in. But we can have diols, where we have CH2s. CH2, sorry. I hope I don't mess this up. Be pretty silly. That would be super soluble, and you would have no problem seeing the solubility of something like that because each of these OHs can carry about 5 to 6 carbons. So this would be, have twice as much solubility than its regular alcohol. So let's take a look. Methanol would have infinite solubility, ethanol infinite, propanol infinite. Well, here we start with 4 carbons. It's not nearly as soluble, only 8 grams per 100 milliliters. So this is where your eyes start having a hard time. Pentanol, 5 carbons, okay, about 2.3 grams. So we're definitely seeing a decrease. And I don't know what it is offhand for 6 carbons, but it definitely decreases as we get those other nonpolar regions in there. So what are our typical, types of bonding that we see within organic and inorganic compounds? So bonding within, and I have mentioned this is kind of a review slide from what we just talked about. So bonding within, this is the intramolecular forces. Organic are usually covalent, and inorganic, we see a lot more ionic compounds. Forces between molecules, these are the intermolecular forces. These are generally weak, and with inorganic compounds, they're quite strong because, again, they have ions. Normal physical state, if you look at organic compounds, they tend to be low melting solids, liquids, or gases because they have generally weak forces. So they're going to have low melting points and boiling points. Whereas organic compounds have high melting points and they're going to generally be solids at room temperature. Now, flammability is a different story. Most of our organic compounds tend to be flammable, gasoline, that kind of stuff. But inorganic compounds are generally non-flammable. Oh, also, TNT, that's popular. All right, solubility in water, very low usually for organic compounds and often high. Again, ions are present in inorganic compounds. It's going to make them really soluble in water. And we have a lot of nonpolar things that come up in organic chemistry. Will they conduct electricity? Well, if they have ions present, for sure they will. So inorganic compounds tend to be much better conductors than our organic compounds. And how fast do the reactions go? Well, inorganic compounds are generally very fast, but we do have some exceptions, right? These are just in general. And organic reactions generally are very slow. So we're going to notice something that happens when we start talking about biochemistry, where we have um, enzymes, and those are going to be our catalysts. So we do need a catalyst for most of these. So we'll talk about different catalysts that are needed for our reactions. However, we do have very practical uses for many of the compounds, especially in nature. So nature is actually really great at protecting itself. So, they do add a lot of chemicals to our produce and things like that, and they shine them up. But plants actually use insoluble alkanes to their advantage. They can produce these really long carbon chains, so like C27H56, C29H60, to protect themselves from bugs and other things. It minimizes water loss and protects them from other things being able to eat their way through. And so, like, if you look at large leaves that do get a lot of sun, or are really thick type leaves, broccoli leaves, cabbage leaves, I think I just said leaves, I'm sorry, leaves, C29H60, they have that waxy type coating on them that they produce to reduce the amount of water loss, and also sometimes they can use it as a protectant from too much sun, because too much sun can cause the leaves to get sunburned. So some definitions, all right? Organic compounds are hydrocarbons. I haven't really used that term yet, but they are hydrocarbons. So hydrogen attached to carbon and other things are called hydrocarbons. Hydrocarbons, a compound containing only carbon and hydrogen. A hydrocarbon derivative is going to be something that contains carbon, hydrogen, and one or more other elements. Like we talked about, phosphorus, sulfur, oxygen, nitrogen, those ones. Saturated hydrocarbons, those are the ones where there's only single bonds. Unsaturated hydrocarbons contain multiple bonds, so we have double and triple bonds. There's no quadruple bond though, so just anything over that has more than a single bond, double or triple, is going to be considered unsaturated. At least you've heard those words, we talk about them with fats and other things. Now, we talked about a carbon can form many different types of compounds. So it's unique. It can form 4 covalent bonds. That is unique. Bonds covalently to hydrogen, nitrogen, oxygen, phosphorus, sulfur, and all the other nonmetals except the noble gases, which until 1963 were called the inert gases for a reason, because they don't like to bond with anything. So the only ones that they bond with are going to be like fluorine, maybe chlorine once in a while. But carbon can form very long chains with itself. It can also form rings with itself. So this is what allows us to have 10 million plus compounds because of all these different unique things about carbon. So one reason that carbon can make so many compounds actually is it can form those covalent bonds. And even though it appears to only have 2 unpaired electrons. So this is actually part of what you should have studied called valence bond theory, is the one that this is focusing on. You may have also talked about molecular orbital theory. So if you want to look at those, you can look at those. But what we think happens if using valence bond theory is that actually we promote one of these electrons up here to the p, and then these 4 orbitals mix together to form 4 new hybrid orbitals that are called s, because we use this one s, and p3 in this case because we used all 3 of the p orbitals. So now we have 4 singly occupied sp3 identical hybrid orbitals that are available to bond. Pretty unique. So what do those look like? Well, we have a normal p orbital that looks like a dumbbell. So this is a dumbbell shape. But then when we hybridize it, this is actually how it's drawn to fit better in pictures. But it probably looks something more like this with a bigger lobe for the S because the S is a sphere. But they try to fit it, you know, on a screen or in a picture. So we represent it more like that bottom picture. But when it can form those 4 bonds, it does so by pointing them as far away from each other as possible. So how it does that is if you have a tetrahedron. So this would be like the 4 points of a tetrahedron. And they point as far away from each other as possible, which ends up being 109.5 degrees in an sp3 hybrid. So there are not all of our carbons are going to be sp3 hybrids. This would be in our unsaturated, excuse me, please forget I just said that. This would be in our saturated compounds where there's all single bonds. So we see all single bonds there. Now when carbon is bonded to 4 substituents, it has, again, it points to 4 areas of the tetrahedron, and they're all 109.5 degrees. But carbon is unique. It can bond to itself, and it can bond to itself multiple times. It must have a total of 4 bonds, so always double check. Double check your answer. Double check. Make sure, count. I didn't mean to do that. Count the number of bonds you have, and you should have 4, always. Okay, that's I'm done with that. All right, so we can bond it to itself. We can double bond to oxygen. We can double bond to nitrogen, but we can also triple bond to itself. We can triple bond to nitrogen, and we can form rings. So these would be unsaturated carbon compounds. Unsaturated is when we have 1 or more multiple bonds. Carbon, I drew this on one of the previous slides, but they can also form isomers. So if we have C4H8, there are 3 different structures with C4H8 that I can show you right here. All of these are C4H8. In fact, I think I could even draw one more. Let's see, CH3, C, 1, 2, 3, 4. Got to make sure I only have 4, bonds to carbon. So that should be CH3, right? 3, 6, 7, 8. Yep. C4H8. And everybody only has 4 bonds as long as I'm looking at that correctly. So there are multiple different types of isomers. These are called structural isomers, meaning they have a different structure. So they all have the same formula. They have different structures. They have different names, and they have different physical properties. So they have different properties. Why do they have different properties? Well, let's take a look at pentane, for example. So pentane, this is pentane. This is isopentane. That's an old naming system, by the way. So this is 5 carbons. 1, 2, 3, 4, 5. And I'm going to just do this because I don't feel like drawing them all out. And the faster we get to do line structures like this, 2, 3, 4, 5, the happier I will be. So I'm going to start doing them now. Isopentane means that we have a carbon 2, 3, 4. 1, 2, 3, 4. One of our carbons is here. So that is the same the same formula, but a different structure. And neopentane actually is 1, 2, 3, 4. So 1, 2, 3, 4, 5 total carbons, all off of that same central carbon. So 4 coming off the center. I don't want to leave that numbering system there because I'm going to teach you how to number later, and that has nothing to do with it. I was just trying to show you how many carbons we had. So what happens is if you look at these space-filling structures, which is why I put these ones in there, because you can see this one's long and branched, right? It's long. This one's got a small branch to it, but it's not too bad. And this one is basically spherical. And I'd like to ask you, if I had to make you pick up some things, if I had like a hard surface floor and I dropped some spaghetti noodles on it that were dry, and I had also dropped a thing of beads that were small spherical beads, which one would you like to pick up? So these are like small spherical beads. And these are kind of like spaghetti noodles. I can't spell spaghetti tonight, can I? Oh, I can maybe. Okay. Well, I would much prefer to pick up spaghetti noodles. I don't know about you, like kind of like pickup sticks, you know, they just kind of like lay there, they don't do much. Where these little things are going to go rolling off under the counter. Having 2 little girls, I know that going and chasing after beads isn't fun. Stepping on them in the dark is not fun. And so these small spherical beads are not going to be sticking to each other very well. Well, remember, the more our molecules stick together, the higher their melting points and boiling points are going to be. So these are going to have a higher opportunity to interact with their neighbors and become entangled, where these are not. So they're going to have lower boiling points and lower melting points, and you know, the density even changes a little bit. So we can see, because they're going to pack well together, they're going to have a tighter structure, and they're going to be a little bit closer together when they're there, but they're not going to stick together very well. I think you get it. Moving on. All right, so we went over, what did I say? Oh, I was just showing you models. All right, just another flow chart. Again, hydrocarbons. We now have 2 different types of hydrocarbons. We have aliphatic and aromatic, and you need to know those 2 terms for sure. You're going to need to know all of these terms. And under aliphatic, we have alkanes. These are our saturated compounds. And alkenes and alkynes, these are our unsaturated. Don't worry, you will know that by the time we're done. Now, under aromatic, we also have a term called an arene. An arene contains a benzene ring, and this is one way to draw that, and there's going to be 5 or so different ways to draw that. This is one of them. This is one of them. So benzene is very, very special. We will have a whole chapter where we talk about benzene, so don't worry. But we're going to keep talking about these different types of structures. So alkanes. Alkanes contain only carbon-carbon and carbon-hydrogen bonds. So these are hydrocarbons. But they also only contain single bonds. They are saturated. There are no functional groups. You haven't even learned what a functional group is yet, but there are none of them present. So these are just a few examples: ethane, propane, and cyclohexane. Now this is LP gas. What does LP stand for? Liquid propane. The only reason it's a liquid is because they put it under pressure. Otherwise, it would be a gas at room temperature. This is a cyclohexane. Also looks like maybe a Ferris wheel, right? This is a cyclic alkane. This does have 1 degree of unsaturation to it to form the ring. So if you see, we have, let's see, you know what, I'll talk about it. I'll talk about it in the saturated chapter. I don't want to continue. I don't want to make you do that now. Sometimes I get off on a tangent. I'll try to stay not on a tangent. Alkenes, oh, sorry. I thought we were going forward. Maybe not. Okay. Alkenes have at least 1 carbon-carbon double bond. So ene means there's a double bond present. This is ethene. Ethene feeds all of our, basically for all of our, what am I trying to say here? Wow, our polymers. Thank you, brain. So my all the polymers that we go into is just like a feedstock for polyethylene and many of the fabrics and different things that we wear. But also in nature, if you look at this giant molecule, and I'll erase that word there, this is actually made by the silkworm moth as a sex attractant. So if you ever are near a silkworm, be careful. All right. And then alkynes, YNE, means there's at least one triple bond present. So acetylene, this would be something maybe you use if you weld, or I used to work for air gas, so we used to fill the cylinders for welding, things like that. So these are anything we have before we have a functional group. These are our main structures, and then what's coming off of them are going to be called functional groups. So functional groups are what we're going to talk about next, where we have an atom or a group of atoms that are in a molecule that have a very specific characteristic set of that are properties that are physical or chemical or both. They're going to be important. So they undergo, this is what's going to help you like memorize the reactions they undergo. They're going to undergo the same type of chemical reactions no matter what organic molecule they are found in. So no matter what they are found in, they're always going to undergo the same type of chemical reactions if the criteria needed for that reaction is met. So large part of what's happening here is they're going to determine the chemical and the physical properties of an entire molecule if they're present. And so functional groups are going to be extremely important. They can actually divide organic compounds into different families. So we're going to see those different ways they work together. You're going to see the chapter names to start with, but they also provide us a basis so that we can derive names for our organic compounds. So when we go through our naming, we're going to go through our naming by functional group. So these are some of this, actually 7 of the most common functional groups that we have. This is an alcohol, OH, an amine, NH2, aldehyde as CO. We actually write it CHO if we're going to make this a shorthand or condensed, so it doesn't get confused with an alcohol. So we'll talk more about that. This is a ketone, this is a carboxylic acid, an ester, and this is an amide. So we will talk about each of those individually. Right now, I'm going to go through a very quick, very brief overview because at this point, at the end of this chapter, I want you to be able to recognize them. Just recognize them, okay? So start with alcohols. Alcohols, OH. Most of you probably have seen these in some type of can, but now with all what's going on, we probably see them in a lot of hand sanitizer as well. And if you're using hand sanitizer that is less than 63%, or well, probably down to 60. So less than 60% alcohol, you're not doing anything to kill the virus. So make sure that you're using hand sanitizer that's at least 60%. You know, what the heck, go up to 70 if you can get it. All right, so alcohols are going to be our OH group, and this is what they look like in this structure. So when we talk about alcohols, we can actually classify them, and you might have to be able to classify them. So classifying them and identifying them by the end of this chapter would be good. So primary, secondary, and tertiary. So primary, this would be a primary alcohol here because this oxygen is attached to this carbon right here. So when we look at alcohols, since oxygen can only have, that says only 2 bonds, we look at the carbon it's attached to. So we're looking at this carbon. How many carbons is that attached to? 1. So it's primary. This carbon, which is attached to the oxygen, is attached to 2 carbons, so it's secondary. And this carbon that's attached to the oxygen is attached to 3 carbons, so it's tertiary, and that's as high as we can get. With alcohols, we can also have what's called a phenol, where we have a benzene ring with an alcohol coming off of the benzene ring. So that is a phenol, and it's very different from what we're going to call a phenol. I forgot the N. Sorry. Good times. Phenol. So phenol, you're going to hear me pronounce it that way on purpose because I don't want you saying phenol because those are completely different groups. So we want to make sure that we're not saying phenol. It's not just like tomato, tomato. Phenol means this particular functional group. Ethers, here's my bad chemistry joke. They have an R group, and I'll tell you what that is in a minute. It's a carbon group, actually. I'll just tell you right now. It's some other type of carbon group. They have an R group on ether side. Oh, thanks. I'll be here all week. Okay, so they have an R group on ether side, and you are going to look and see that here. What does this mean? An R group can be any type of alkene, alkyne, alkane. It can be an aromatic or a regular aliphatic. So aliphatic or aromatic can be two aromatics. Either way, so AR is a carbon group. It is also an R group, but we're just designating that it's possible because some of these functional groups, it's not going to be possible to have an aromatic. So we want to make sure we go through the difference on those. Now, with phenol, okay, so we have phenol. We also have diethyl ether, which used to be used as an anesthetic, but it's also very flammable, so we don't really use that anymore. But in a pinch, be careful. Don't have anything else. But, having an oxidizer or oxygen present near a flammable anesthetic is not usually a good combination. We don't want to light our patients on fire. It hurts. Okay, alcohols is where it's at, is what we've been talking about. I want you to pause the video, and if you don't pause it, it's on you. I want you to draw the Lewis structures and the condensed structural formulas for the two alcohols with the molecular formula C3H8O. So pause it, do it. I'm not going to wait because otherwise the video will be like 90 minutes long. All right, so the Lewis structures, and I'm actually just going to click through because I'm not with you. Oh, I guess I can draw them. The way I like to do these is I like to draw the carbons in a line. 1, 2, 3. I'll draw my hydrogens. Let's see, CH2, and then I'm going to put my oxygen in there with an alcohol. So I did say that they were two alcohols, so there does have to be an alcohol group. Well, where else could this alcohol group be? It could be, let's see, it could be here on the second carbon. So we have two options for where that alcohol group could be. It can be on carbon number 1. I'm sorry, that's 3, 2. Carbon number 1 or carbon number 2. And notice in this compound, it doesn't matter which way I number it, but this one it will. The alcohol gets the lowest number. We'll talk about that later. So that is, those are, excuse me, now they're the Lewis dot structures. Come on, Professor DeVos, don't forget your dots. And in the condensed structural formula, I would want to see CH3, CH2, CH2OH. And how do we do this with the one where it sticks up? You can say CH3, CH, CH3. And you can put a line that says OH, that's okay. But you can also say CH3, CH, OH. And you don't even actually have to have the parentheses. We understand that it has to go up or down. But I find that most people find this way easier, and I don't mind either way. All right, next up is amines. Oh, sorry. Actually, let me go back and erase my crap here. So can you see that? Okay. So that you guys, seriously. Stop it. You see it moving on me? Okay. Okay. There we go. So this is what this is called. This is a primary alcohol, and this would be a secondary alcohol. So amines are a compound that contain an amino group. So they have a nitrogen group in there. Now that nitrogen can be attached to one R group, 2 R groups, or 3 R groups. Those R groups can be identical, they can be different. They can all 3 of them be different. So an amino group can also be classified as primary, secondary, and tertiary. When it's attached to one, now look, this one we look at the nitrogen directly, it's attached to one R group, it would be primary. 2 R groups, it's secondary, and 3 R groups, it's tertiary. Now, why do we look at the nitrogen here and the oxygen? We have to look at the carbon because nitrogen can form up to 3 bonds. So we can do it by looking directly at the nitrogen. The R groups can be alkyl or aromatic, both are possible. So these are just some examples down here. This would be methylamine here. This would be a primary. Dimethylamine would be a secondary. And trimethylamine would be a tertiary. So I want you to try this. I have a note here in mind that you might have a typo in your slides, and I'm sorry if I didn't fix it, but just double check before you guys spend time doing this if you're working on the student slides that you have C3H9N. And so I want you to draw the condensed structural formula for the two primary amines. So there's two different primary amines. Remember, you can start this by doing your 3 carbons. And how can they be attached? Well, the nitrogen could be attached here. Oh, pause it if you haven't paused it and try it. This is where you get to try it. Or the nitrogen could be attached at the second carbon here. Now, why can't I come back here and say nitrogen, carbon, carbon, carbon? These are actually the same. We would just count this one 1, 2, 3, and we would count this one 1, 2, 3. So they're exactly the same molecule. So this is the same as the one you already drew. So these are the two primary amines. When it says practice or you try, make sure you're pausing the slide and trying it. Okay? All right. So next up, we're going to see amides. Amides are similar. They have a nitrogen, but you know what they don't? What they have that the other one did not? Is they have right next to them what we call adjacent to them, they have this carbonyl group. So this double bonded oxygen makes this an amide. It gives them very different properties. So these are very different properties than an amine, and we will talk about that in the different chapter. So all of these R groups can be carbon or hydrogen. They also can be any type of R group is possible there. So I do like to be specific when it can be hydrogen because not everything can be hydrogen. So this is an amide here for an example. This is Tylenol. This is acetaminophen. So we see an R group here, and then we see our double bonded oxygen, our carbonyl group bonded to our nitrogen here. So what type? We'll talk more about that later. So this is Tylenol. Tylenol is an amide, or has an amide, contains an amide. It also has what? What's this? A phenol. Yeah. Okay. So we have multiple types of functional groups that can be in each molecule. That's okay. Now, aldehydes and ketones both contain a carbonyl group. Aldehydes, it's on the end, so we write that CHO. So this is how we have it, but it's on the end. It's always terminal. It's the first carbon. And a ketone is internal. So we see that double bonded oxygen, but it's always internal. It cannot be carbon number 1. So I want you to practice. I want you to draw the condensed structural formulas for the two aldehydes with the molecular formula C4H8O. So please pause it and try it. Otherwise, you're not going to get much out of this if you don't pause it and try it, okay? So the functional group would be, let's see, what are we doing here? We're doing aldehydes and ketones with C4H8O. So again, I would first draw out the carbon chain, the structure, and then go and add the hydrogens in there. So draw the functional group of an aldehyde, add the remaining carbons, then draw, whatever you need to go from there. Make sure everybody has 4 bonds. So here is this way of writing the condensed structure, or this way of writing the condensed structure for the one. And this is our other one where we have a branch here. This is actually called an iso group. So we have, again, we can put the double bonded oxygen in there, or we can condense it down like this. Carboxylic acids. Carboxylic acids are going to be one of our ones where we can form an ion. So we'll talk more about that later. But in a condensed structural formula, you usually write it as COOH. I don't see this very commonly, but it is possible. I always write COOH. I don't know what other people do, but I've always seen it written this way. And I remember even in Gen Chem, we have, CH3, COOH. It bothers me. This is acetic acid. It bothers me when people write it another way, but you know, even in Gen Chem we learned like this because it's a structural formula. It tells us about the formula. So this is another way of writing acetic acid, and this is what it looks like. So C, a carbonyl, excuse me, C double bonded O, and an alcohol in the same, on the same carbon. So that not just in the same molecule, but on the same carbon gives us a carboxylic acid. So practice this one. Draw a condensed structural formula for, there's only one carboxylic acid with this formula. Pause it, please. Okay, so it would look like this. So the COOH group has to be terminal in this case. It can't be anywhere else. So it must be, I got a lot of typos here, be on an end in the carbon chain. So there we go. Esters, this is an ester. An ester has started from a carboxylic acid, but the hydrogen from the oxygen, so there used to be a hydrogen here, has gone away, and now we have a carbon group there. So now we have an R group there. So now we have basically something that we can break here. And when we look at fats, we have three esters that this is really not even, but three esters that form our fat groups here, our triglycerides. And so this is where we see we have three of these that we can break apart. This is our glycerol backbone, and we end up with being able to break those, and that's how we break down fats, is we're going to break apart that ester. So they're oh, I didn't mean to break that there. They're triesters. Man, I'm tired today, I guess. So this would break between this group right here. And we're not, don't worry about that. I'm just trying to show you what they are, but sometimes I just can't help myself. I get too excited. So acid chlorides and acid anhydrides, these are going to be derivatives mostly of our carboxylic acids. So in this acid chloride, where we see the carbonyl C double bond O, what used to be an OH is now a chloride. And when this comes together, actually we have two of these on this one, and this is called hexanyl chloride. This is a precursor for making nylon. So when we have a precursor for something that is going to be a polymer, we usually see it on both sides so that we can build outward from both sides of that and make the polymer twice as fast. And then the acid anhydrides always have the C double bond O, the carbonyl, then an oxygen in the middle, and then a C double bond O. Now, we can have them like this, but we can also have different, and not just, you know, carbon and oxygen. So we will talk about these in a couple different ways, and I will talk about that when we get to that chapter. So we have R groups, R1 and R2. Usually they're the same, but they don't have to be the same. So usually they are. This is acetic anhydride. This is something that we actually use to make esters. So we can actually, like, you know, break this apart, and we can have two different groups that come on. Now we always break between the oxygen and the carbonyl, but we'll talk about that when we get to the chapter. We actually already had amides, but I have an amide chapter, or amide slide in here again. Sorry about that, but hey, you get it twice. I just felt like amines and amides needed to be close together because they both contained nitrogen, I guess. But so here we have our amide groups. Thiols. Thiols are smelly. So actually, a skunk sprays a thiol. I mean, they're very, very smelly. They're also called mercaptans. So if you go into an industry and there's a bunch of old people that have been working there forever, they're going to call them mercaptans. You might see it in literature that way. So it is still very common to call things mercaptans. It's not something that's just outdated. I mean, it is outdated, but you still see it out there. So this is any SH group, SH. Now we can also have disulfides. These are extremely important. So cysteine is one of our amino acids that forms forms disulfide bonds like this. And if you have curly hair or if you have straight hair, it's going to often have a lot to do with these cysteines forming these disulfide bonds. So this is cysteine, your amino acid. cysteine that can actually form this disulfide bond with an adjacent cysteine, causing the folding of your proteins. So those need to happen appropriately. All right, that's it for the functional groups in this chapter. I want you to practice. So these highlighted ones, I want you to go and identify. Don't do that while I just gave you number 1. So just write, 1 through, what do we have? 1 through 9, 9 down, pause it, and I'm going to then click through it for you. So number 1 is an amine. Number 2 is a carboxylic acid, COOH. Number 3, we have our carbonyl with an oxygen and an R group here. That's an ester. Remember, an ether doesn't have the carbonyl. An ester has the carbonyl. This is an alkene. Number 5 is an aldehyde. Number 6, an alcohol. Number 7, a ketone. Number 8, a thiol. And number 9 is an anhydride. So hopefully you did well. We'll be back with the next chapter soon.